scoring every user item pair does not scale. A PyTorch 2 tower model learns separate user and item embeddings, so clicks become retrievable candidates. You'll learn how the pieces fit into a workflow that learns from user choices and finds nearby candidate items quickly. I'm Professor Pi, teaching AI foundations with simple Python. 2-tower retrieval answers a real engineering pain. When you have millions of items, you can't score them all at request time. Instead, you pre-compute item vectors, compute a user vector at query time, then find a small set of nearest item vectors and hand those to a heavier ranker. That keeps latency predictable and lets systems serve many requests per second. Think of users and items as points on the same map. Similar tastes cluster together. If a user liked item A, the model nudges the user's point toward A and pulls A closer to that user in embedding space. The 2 towers let user and item representations be learned separately so they can be computed independently and cached. We'll build a tiny transparent example that learns from positive clicks and then finds a few nearest items for a single user. The code stays small, so you can see the data flow from raw events to candidates. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we convert human-readable interactions into numeric tensors for training, so PyTorch can work with them. This snippet turns tiny readable interactions into PyTorch tensors for training. Recommenders start from events like AnnaClickT, but models need compact numeric IDs, not strings. The dictionaries, UID and IID, keep that translation explicit. While batch U and batch I hold the positive user item pairs we want the model to pull together. Nothing is ranked yet. This is just the clean handoff from product data to tensors. The output confirms the batch has real positive pairs and that the item ID still maps back to a human-readable item. Next, we need a model that converts those IDs into vectors, so similarity makes sense. This example builds the 2 towers with PyTorch nn.Embedding and compares one positive pair. The user tower converts user IDs into vectors, and item tower does the same for item IDs, so each side can be computed independently. Torch.nn.functional.normalize makes the dot product behave like a direction match, which keeps the score easy to interpret in this toy setup. The small manual weights are just for a clear first screen before training changes them. The output shows one aligned pair has a high similarity score, which is the basic signal retrieval we'll use later. We also need a loss that teaches the model to prefer the true item over other items in the batch. This code trains the retrieval idea without listing handmade negative examples. The matrix logits compares every user vector in the batch against every item vector in the same batch. Target says the correct item is on the diagonal, so torch.nn.functional.crossentropy rewards the diagonal score and treats the other columns as in-batch negatives. The 4.0 multiplier sharpens the contest. Making it larger makes confident matches matter more, while making it smaller softens the differences. The output shows the current batch ranking and the loss that training will try to reduce. Now, we let gradients update both towers, so the vectors actually move toward better retrieval. This snippet lets PyTorch actually move the 2 towers instead of just measuring them. Opt includes parameters from both user tower and item tower, because retrieval only works when both vector spaces learn together. Each loop rebuilds normalized embeddings, recomputes the in-batch logits, backpropagates cross-entropy, and applies torch optimatum atom. More steps usually give the optimizer more chances to separate positives from negatives, but they also add training time. The output shows the loss moved down, which means the towers are becoming more useful for candidate retrieval. Finally, we use the learned item vectors to generate a short candidate list for a user at request time. This code performs the candidate generation step the whole tutorial is aiming for. Item index represents item vectors that can be computed ahead of time, while query is the one user vector we need at request time. The score line is still a tiny matrix multiply here because the catalog has 4 items. In a larger system, this same embedding layout is what a vector index would search. Torch.topk keeps only the strongest matches instead of passing every item to a heavier ranking model. The output shows a short candidate list for Anna, which is the retrieval stage doing its job. If you map this toy example to a production flow, item index becomes a persistent vector store, and query vectors are computed per request. You would swap the brute force topk for a FAISS or ScaNN index when the catalog grows. The training loop and the in-batch negative trick stay the same idea, but you add more users, more items, and logged regularization. 3 quick points to remember. It learns separate user and item embeddings, so retrieval is fast. Use it when your catalog is large and you need low latency candidate generation. One caution is index freshness and cold start items, which still need special handling. To push this further, index the item vectors with FAISS and tune nlist and nprobe on a real dataset like MovieLens 100K to balance recall and latency. That single change will show how embedding quality and index parameters interact in real traffic. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.